Hello all. Today we'll be looking at linguistic variables. So we know that variables in mathematics normally takes numeric values, but when dealing with fuzzy logic and fuzzy set, we can say that there's a possibility that linguistic variables they usually take non-numeric values. So when we talk of non-numeric values, they are not numbers; they are but words or sentences from a natural language. So as an example of any fuzzy set that you can represent, say, for example, the term age. So the term age is basically a linguistic variable. Okay. So you can see, for example, the term age that is used here is used as a linguistic variable and it can contain the values. You can say child, young, old, etc. So you can say linguistic variables are variables with value made up of linguistic concepts. So when we say linguistic concepts, those are words which describe that, or there are types of words that can describe that particular linguistic variable. So you can say rather than numbers, we'll have words like child, young, etc., etc. And they can also be variations of these things. So as an example, we can see that the graph that is shown here shows uh, each of the linguistic phase. It starts from, say, you can say the age in x-axis goes from 0 to 100, and on the y-axis you have the membership values of each of the type that varies from the range of 0 to 1. So these membership functions can then be used to identify whether the person is a child, a young person, or an elderly person. You can see each of the fuzzy term, that is, each of the fuzzy term child, young, and old is described by its membership values using this graph. Say for example, you can see a person is a child or a human being that is shown as a child. If the value varies from 0 to 10, and it is the completely in the membership value 1 when the value varies from 0 to 10. Suppose that the age is 11. Okay, so you can see when the age is 11, we'll get a membership value of 0.75 roughly. It is identified by the mark that is shown there, 0.75 roughly. So in the child set, we get 0.75. But whereas in the young set we get zero point 0.2, and in the old set we get a value of 0. So if a person's age is 11, it is safe to assume that he or she is a child, but perhaps a little young, but certainly not old. Okay, so that is the basic idea. Now, a linguistic variable is a fuzzy variable. You can say, for example, the statement John is tall. Okay, implies that the linguistic variable John takes the linguistic value tall. So the range of possible values that this linguistic variable represents is known as the universe of discourse. We have already seen this term earlier. And say, for example, if you take the linguistic variable speed, then the universe of discourse will be maybe 0 to 220 kilometer. For example, in the previous one, here the universe of discourse was 0 to 100. That is a range of possible values that it can take. And it can have an age had fuzzy sets or subsets like child, young, old, etc. So when you when you think of the linguistic variable speed, we may have fuzzy subsets such as very slow. You can see here, very slow, slow, medium, fast, and very fast. So these are also possible. So basically, you can talk immediately, or on the first round, you can just think of slow or fast as the basic values. But there are possibilities like you add these terms like very slow, then you may have also medium. Okay, you can add medium also here, medium. Then you can also add very fast. So the term very is added to the existing values. So, if a linguistic variable carries within the concept of a fuzzy set qualifiers, then we call it as a hedge. So, what we are actually talking of in this slide is linguistic variable as well as hedges. So, what are hedges? Hedges are terms that modify the shape of the fuzzy set. So, they usually include adverbs like very, somewhat, quiet, more or less, slightly, etc. There are many possible hedges. So you have a set of values, and along with that, you're adding some adverbs to modify the shape of the fuzzy set furthermore. So, for example, just a second. The possible range, you can say the values can come up to, say, you can have all-purpose modifiers such as very, quiet, extremely. You can have truth kind of values like quiet, true, mostly false. You can have probabilities like likely or not very likely. You can have quantifiers such as most, several, or few. Possibilities like almost impossible, quite impossible, etc. So hedges, they act as operations themselves. For example, very means what? You're adding something more, and it is actually a new set of subset. So for example, I'll show you in the PPT. If you're taking a value that is height of a person, if you're talking of a, what do you say, the linguistic variable height of a person, these are the different values that it can take. So normally we have short, average, tall, etc. So suppose you're adding very short, this is how the graph will look like. If you're adding short, this is how the graph, you can see very short is this particular graph, short is this, average is this, okay. Then you can say tall is this, very tall is this. So you can see tall has a distinct line like this, see, but very tall goes like this. So similarly, and here also you can see, I'll just change the color of the screen. Short is described like this, but very short is like this. You can see when short is having a graph like this, very short will go like this. It's much more steeper, you can say. Okay. So it actually reduces it, the value. So even though you're saying it is very short, so it's actually reducing the value. So this is how we go. This way you can modify the shape of the graph. So this is actually done with the help of some transformation functions. It's not directly given in our syllabus, but we can look into it. So if you have from the set of Tolman, we can derive the subset of very tall. That is what it indicates. So very means it performs a transformation known as concentration, and it will create a new subset. Similarly, if you have something known as extremely, it is also serving the same purpose, but to a greater extent. And opposite of this concentration operation is something known as dilation. Okay, so if you have more or less Tolman, or you can do dilation or something like that. So there are many operations or hedges like this, where you can have, say, other hedge for describing temperature. I can say is very cold, moderately cold, slightly cold, neutral, slightly hot, moderately hot, very hot, etc. So obviously all these fuzzy sets can overlap. Okay, that is how we cannot actually distinguish between slightly hot and moderately hot. That is a human way of thinking. The same thing happens here also. Okay, so if you look at this graph once again, you can see that as an example, consider a man who is 185 centimeter tall. Okay, he is a member of the tall set with a degree of membership of 0.5. You can see in the graph. But however, he is also a member of a very tall set with a degree of 0.15, which is reasonable. So that is the basic idea. Now, how do we do these kind of things? We can look at some more examples and move forward to the transformation. I'll just give an overview of what are transformations. So this is a example of how a hedge a little can be mathematically expressed. Okay, it's basically raised to 1.3. Slightly is the membership value raised to 1.7. Very is a membership value raised to 2. Extremely is the membership value raised to 3. You can see as the value increases, the graph will go, what you say, it will go very pointed towards, you can see over here, the point or the rounding feature here is very less, but when the value increases, it becomes very pointed, but it goes in steeper like this. Okay. So it's another subset of the previous set. Very, more or less is the opposite. So Till now, this were the one kind of thing. Now, if you have more or less or somewhat or indeed, you can say the pointing feature goes and it becomes more rounded kind of feature. So here we are actually raising it to the power and here we are reducing. So we were taking square root maybe, or we are subtracting by 1, or we are doing something even lesser value than that. Okay. Some of the transformations are shown here. You can see the common one that we usually use is the second and the third one. I'll discuss on that. Some of the possible transformations are normalization, dilation, concentration, contrast, intensification, and fuzzification. So these transformations actually change the shape of the fuzzy set that we know. So what does a normalization operation do? It converts a subnormal fuzzy set to a normal fuzzy set. We know already what is a subnormal fuzzy set. So it converts it to a normal fuzzy set. So it is obtained by dividing the membership value by the height of the fuzzy set. So suppose you have a fuzzy membership function for a particular value x and you divide it by the height of the fuzzy set. So when you do that, what happens is it converts a subnormal function to a normal. So when you apply a norm, this is what happens. When it becomes a normal, it always touches 1, right? So you'll have at least one value with the height of 1 there. So that is what happens. Okay. Now dilation. This operation flattens. You can see the operation is what we saw in the previous examples of dilation. This one actually flattens the membership function so that it attains relatively higher value. And what happens is the overall shape of the membership function gets dilated. So after dilation, it is actually flattening. So it was more point. You can see the earlier graph was more pointed, but now it is going more. So it is actually flattening the value, but you're getting relatively higher value. Even though the graph looks flattened, but the value is relatively high. So you can see, in other words, the resultant function is less pointed around the higher membership values. So it is less pointed. Earlier it was much more pointed, but now it is being flattened like this. So I'm drawing it outside only, but this you can just look at the dashed line. That is the output that we get after applying. And it can be done by maybe raising it to say, you can find the square root of this membership value. That is one way of applying this, the effective shown here. Okay. Now another one is concentration. So this is the reverse effect of dilation. Here the function attains relatively lower values and it gets more pointed around the higher membership values. So you can see earlier it was like this. Earlier it was the outer one, the solid line that you see, it was like this. But now it attains a relatively lower value, but it gets pointed towards the higher membership function. So when it reaches a higher membership point, you can see it narrows down. So that is known as concentration. So you can see concentration can be done by raising it to the power. The membership function can be squared or cubed or something like that. So that is what I showed over here. You can see all these are concentrations. See, look at these are concentrations. So they are showing slightly, very extremely. So as the rate increases, this is known as concentration. But if you do not know what is the exact thing, you can actually get relatively higher values by looking at the square roots or something like that. Then contrast intensification is not so important, but you can look at this as the formula that is applied that we saw there for indeed 2 into membership function raised to 2 if the value of the membership falls between 0 and 0.5. Otherwise, you just subtract it with 1 minus 2 of 1 minus the membership function the whole square times 2 and the entire thing is subtracted from 1. So this is how it goes. You can see the difference in graph, see how it goes. Around this, it goes down, but around this, it goes up, and so on. So you'll have two kinds of values here. So contrast intensification is by reducing the membership values that are less than 5 and elevating those values that are greater than 5. So that is why you have two sets of equations. Fuzzification is the opposite of this. Here, when the membership values are less than 5, see this one, when the membership values are between 0 and 5, those will be elevated, while those that are more than 5 will be reduced. So if the membership value falls between something like this, those are elevated, you can see. But with the ones that are above this, sorry, yeah, the ones that are above zero point 0.5 will be reduced. That is why the graph is much more pointed here. So talking of linguistic variables once again to wind up, the transformations that we saw earlier are very useful when we are dealing with linguistic variables. Linguistic variables are just what the variables that we use for defining a, you can say, a fuzzy set. So conventional variables usually have, numeric or alphanumeric string values. But in this, we have phrases or words. Phrases means very tall and etc. So, or you can have simple words like tall. So each of these linguistic values correspond to a fuzzy set. So when you look at the variable height, okay, so suppose you're looking at the variable height, then you can see that um, if it was a conventional variable, you would have a numeric value there, but we're not having a numeric value. Uh, just a second. Okay, we are not having a numeric value. And but as a linguistic variable, you can have the values like short, average, tall. So those will be the predefined words we'll be using. Now consider the attribute very tall. We have shown the graph for tall and very tall here. So the word very may be viewed as a transformation applied to the meaning of tall. So if you have a linguistic value tall and you're applying an extra feature on that for showing very tall, right? So what we can do with very is the word very is we use the help of a concentration operation. Okay. So reason is that concentration reduces the magnitude of the membership value. You can see how the graph goes down. Okay. You can see how the graph, just one second. You can see how the graph is much more steeper than very tall is much more steeper than tall. Okay. So you can say that what tall is to some extent might be thought as very tall to a lesser extent. So the membership function for very tall should always be less than that of tall. That is how it should be. Okay. Moreover, the transformation from the lower part of very tall to the higher part of very tall, you can see when you look at the lower part of very tall to the higher part of very tall, it will be very steeper than the transition from the lower part of the tall graph to the higher part of the tall graph. So you can look at the straight line. So you can look at the straight line. The transition at the lower part here, the transition at the higher part here is different for tall and very tall. So very tall, it is much more steeper like this. It goes down. Okay. So it's much more steeper. So that is what this idea of this graph means. Now, and there are some more examples with this. We'll discuss for that with the help of another slide. I'll show you. Okay, this is an example given in the textbook. Uh, Consider a fuzzy set with a triangular membership function defined on the interval -2 to +2. Okay, so the membership function values, they have given the formulas like this. Like if the value of x is between -2 to -1, it should be 0. And if it is between 1 and 2, between 1 and 2, then also it is 0. Otherwise, if it is between, you can say -1 till 0, then you can have x plus 1. Or if it is between 0 and 1, you can say it is 1 minus x. So the shape of the triangular function, you can say we can apply all these kinds of transformations and see how the output looks. So according to the equation they have given, the shape of the triangular function will be something like this. See, you can see from here, when it is -1 to 2, it is 0. When it is 1 to 2 also, it is 0. But the rest of the values, it goes sharp to the point 1 when it is x plus 1. And otherwise, it goes 1 minus x when it is between 0 and 1. It goes sharply down towards 1. So hence, it becomes a triangular function. Okay, a proper triangular function. So since the height of this is 1, normalization, you know what is a normalization effect? A normalization effect, as we learned earlier, say in our example, it dividing by the height. So already we have the height of 1. So there is no need to perform a normalization again because the triangular function is already having a height of 1. There's no difference there. It will have no effect. But other things like dilation, concentration, all these, you can see the outputs are shown here. So if you are applying those kinds of formulas for dilation, maybe you will get a rounded, more flattened graph like this, a rounded one. When you do a concentration, you can see it goes more steeper, something like this. And when you're doing contrast intensification, it will have two different shapes. For values less than zero point 0.5, it will go inside, whereas values greater than zero point 0.5, it will go outside. It will have a more reduced kind of shape, that is a flattened kind of shape. And fuzzification, you'll have a more pointed value towards when it goes towards 1. Otherwise, you'll have a flattened kind of value. So these are some examples. So you can apply any kind of formula like that. Say these formulas that are given here. Like you can, for dilation, you can take the square root. For concentration, you can take square. Okay, more possibilities are there. These are just some examples. And for intensification between 0 and zero point 0.5, you apply 2 times the square. And otherwise, we take 1 minus 2 times 1 minus the membership value, the whole square, and so on. Similarly for fuzzification. So you can just go through these formulas and try out for other examples also. Okay, thank you.